Hello and welcome to deploying your first SD Access project based on Lisp VXLAN stack, also known as BRK ANS 2824. My name is Sergey Nasonov. I'm a solutions engineer based in Sydney, Australia. In Australia and New Zealand, we have a lot of SDA deployments, pretty much most of the major Cisco customers running SDA, and all of them having the same problems again and again and again. So I decided to make Cisco Live session out of it. All right? So a couple of words about the format of the session. The session is very tightly packed with information. I had to cut a bunch of slides to make it into 90 minutes. I wish I could lock the door and go for 2 hours, but there is another session after this. So while I appreciate the interaction, feel free to ask a few questions. But if I feel I'm running out of time, I'll ask to join the room and post a question there. I'll answer after. Or I'm happy to stay after the session and answer all questions live, as long as you guys have any questions. OK, this is advanced level session, right? This is not basic SDA 101. It's advanced level session. And in order to gain the maximum benefit out of it, the expectation is that you attended at least 2810 yesterday, the SDA basics, or have equivalent theoretical experience. All right? The session is practical, very practical. Every slide there, it's either customer problem or customer question. There are no textbook examples. And as such, it represents my opinion. Different people have different experience, so they form different opinions. So this one is mine. And the trigger for that session was a question from one of partner solution architects. He was like, OK, Sergey, I watched all SDA videos. I read SDA CVD. Where do I start? Well, let's get started, right? So when you're deploying SD Access, it is no different from any other network deployment or network refresh project. And as such, there is a planning stage where you normally produce conceptual or high-level design, detailed design, implementation, or more typically migration, because most deployments are brownfield. And if you're lucky, there would be some lessons learned or debrief at the end, right? So this session will follow the same format. But before I start, couple of things on the vocabulary. Catalyst Center, I think by now everyone knows it's a rebranded DNA center, or DNAC, right? Endpoint, or short for EP. You will see EP a lot in the slides. So endpoint is just a host connecting to the network, right? It's a laptop, it's a printer, it's a CCTV camera. It's something that is not routing the traffic. It's just a host. SD Access, also, some of you might know that there would be EVPN-based solution, also called SD Access, in the near future. But for the purposes of this presentation, SD Access is Lisp-based solution. So implemented by control plane nodes, border nodes, edge nodes, and so on. All right? And group-based policy, just a rebranded TrustSec. When TrustSec is used in the fabric, in the overlays, we call it group-based policy. Marketing exercise, I guess. OK, so what do you need to do when you're planning SD Access deployment? Well, you collect the requirements, right? First, before you even attempt it. Why do we care about requirements? Well, because SD Access as a solution, it has certain limitations that you as a network designer needs to be aware of. There are some appliance-level limitations, right? So Catalyst Center, it's a physical appliance. It has a finite number of CPU cores and RAM and storage. And as such, it imposes some deployment-wide limitations, right? So for example, number of endpoints, number of network devices, interfaces, and so on. Once you drop to the site level, so which is your campus or your LAN, there are two types of limitations, right? There are site-level limitations in Catalyst Center. And because on the site you put real hardware, there are some real hardware limitations, right? So the lowest of the two applies. So all of these limitations are very well described in the Catalyst Center datasheet, which has about 15 different tables, right? But I don't expect anyone, myself included, to navigate all of these tables and crunch all this data first time when you're doing it. It will only make sense in the middle of the deployment, when it is already too late to change the design. So as such, we'll be looking at a case study to demonstrate all of these tables and limitations, right? So meet Acme Corporation. That's a customer case study, so it's a large manufacturing organization. And I managed to collect some of the requirements, right? I looked at the topology. They have large manufacturing site with 3 sub-areas interconnected through dark fiber. They have about 2,000 switches in 1,300 switch cabinets. Number of users, number of devices, 700 VLANs, and so on. A couple of DCs on site as well. And importantly, they also have the remote offices. Think of them as a retail office, single switch, couple of APs, nothing special, but they also need to be part of network refresh. To visualize it, we have the topology. So you will see it on the left side. We have our main campus with dark fiber crossing in, MPLS, all the remote sites on the right side, and the MPLS headends are also in the data center. So the data center is the centralized resource manager, right? So they have on-prem apps, they have internet, and they have public cloud peering, all from the DCs. So once you have a high level of understanding of the number of endpoints, number of switches, number of sites, network topology, the next best step is to use SDA design tool. So it's available on the URL listed on the slide, available for everyone with Cisco accounts, so no entitlement required. Just log in. It asks you a series of questions. And the best thing about this tool that you don't know what you don't know when you're doing a design. But this tool actually, by virtue of asking you the questions, get you to think, oh, did I think about multicast? Where my RP is going? And so on, right? So it's a fantastic tool that after you input or answer all the questions and input all the variables, it will generate you a Word doc. How good is that, right? It's not 100% high-level design, but I would say it's a 90% or maybe 80% of design, right? And it's much easier to add remaining 20% rather than trying to write such document from scratch, especially when you don't know what you don't know. So once you have this document, you give it to the business or give it to the customer. Hopefully it gets approved. And now the next step is detailed design. How would you do that? Well, before we even start thinking about SD access sites, we need to recognize that there are some external dependencies, all right, for any SD access deployment. For example, Catalyst Center, right? That's automation engine for SD access. You kind of have to have it because that's a GUI where you click the buttons and then it goes and configures the network. Rest of dependencies, technically optional. As optional as DHCP and DNS can be, right? I guess there are some networks without it. As optional as ICE can be. So Cisco ICE, while it does authentication and authorization of endpoints, I call it optional because you can use third-party NAC if you want to. You will just lose on micro-segmentation capabilities. Cisco wireless LAN controllers. Again, if you want to use Fabric-enabled wireless, so if you want to integrate wireless into the overlays, you have to have Cisco wireless controller, but it can be any other wireless. All right? And a Fusion device. Note that I use, unlike the Cisco design documentation, I use the firewall as the Fusion, not necessarily a router. Why is that? Well, the Fabric facilitates the creation of campus-wide VRFs, right? Or we call it virtual networks in SDA. And each VRF is a security zone, right? So when you have multiple security zones and you want traffic to flow between the zones, you want to enforce some sort of security policy, right? That's not possible on a switch, on a router, but it's possible on the firewall. If you're not enforcing any security policy, why do you have multiple VRFs in the first place? Just put everything in one, right? Make it simple. So the external dependencies are called external for a reason. They're outside of the Fabric. And as such, there are some latency limits that you need to be aware of. For example, Catalyst Center, to manage network devices, 200 millisecond round trip time. Does it mean that if you go 210, everything falls apart? No, not really. It's just that 200 millisecond is the tested number, tested and supported number. So engineering team will stand behind it. You can go higher, provided you obtain the exception or approval through design council, right? So the other limitation is 100 millisecond for ICE. This is not strictly SD access limitation, it's just a radius protocol requirements. And again, this is something that ICE team had tested and validated. They're standing behind this number. 20 millisecond for Fabric access point to Fabric controller. Again, this is not SD access. Even though the IPs are Fabric enabled, they're still using CapWAP control channel to talk to the wireless LAN controller. As such, this is just a requirement coming from the centralized switching wireless, right? Okay, so we sorted our external dependencies. Now let's look at the first question that is normally faced when I'm talking to the customer. How would you carve your fabric sites? Right? But first, let's think what the fabric site is. Well, you can read in CVD that the fabric site is an instance of an SD-access fabric. It doesn't help much, does it? So for me, the fabric site is the collection of the edge node switches, so the access switches, sharing the same control plane and border switches, or core switches, right? That's typically the fabric site. And typically, it's defined by geographical boundary. Right? So you have a campus with multiple buildings. That's typically a site, but not always. Sometimes you might need to think how exactly you're going to carve it based on the endpoint scale, which I'll touch on, failure domain scoping, underlay connectivity attributes. If you have more than one site, if you start splitting them, you might want to connect them through the means of transit. Right? Could be IP transit or something else. So let's double click on the limitations. Oops, I think I clicked the wrong button. Let's double click on the limitations. First one is the control plane node scale. Right? So control plane is where the list database is located. And the control plane node stores the endpoint information in RAM. And it's using CPU to answer the queries, right? To do the database lookup and answer the queries. Different switches have different scaling parameters. So for example, 9300s can support up to 16,000 endpoints. 9500, more appropriate for the large network, can support up to 80,000 endpoints, right? So this is the kind of information that is documented in this Catalyst Center datasheet that I referred earlier. Specifically, control plane scale is table 7, all right? The border, oh shit, okay, keep clicking the wrong button. Sorry about that. Okay, the border is your egress point, all right? The border also stores the endpoint information, but it stores it in a switch TCAM, so in hardware, in ASIC, right? As a host route. The consequence of that if endpoint has multiple IP addresses, so it's typical in dual stack deployment or IPv6 deployment, then each address is counted as a single entry. So if an endpoint has 3 addresses, then the scaling number needs to be divided by 3, right? So 9300 again have 1600 scale, host route scale. 9500 has 150,000. Again, the sizing value is documented in this datasheet. It's table 8. Apart from scale, you might think about other non-necessarily technical parameters, right, that might influence your decision how you want to split the sites. So for example, remember the definition? All edge nodes in a site are sharing the same set of control plane and border nodes. What it really means is that if all control plane and border nodes fail, your site is failed. No new sessions can be established. All right? So you might start thinking, where is my failure domain is? What happens if all my switches fail? It's typically not a problem in a traditional LAN environment because that would be your core switches. And if your 2 core switches fail, you kind of have failed site anyway, right? Another interesting point is that a lot of configuration elements in SD access apply on a site level. So when you're creating a VRF, it's provisioned to all switches in the site. It could be 1,000 switches. That's a big change. If you're creating an ECAS gateway, again, it's pushed to all switches. Maybe your change control policy doesn't allow it. Maybe your risk tolerance is not that large that you want to push it all the way, right? Then you can start thinking about splitting it. Another interesting point is that the whole fabric is typically underpinned by a single underlay routing protocol instance, be it OSPF or ISIS, as well as the Lisp, obviously, for overlay. And the site is peering using eBGP with the outside world, Fusion, typically. And as such, it's appearing as a single BGP autonomous system number to the outside world. So if your backbone starts dropping traffic for particular BGP ASN, well, then the whole site is affected. So as you can see, it's not necessarily SDA-specific things, but it's a general network design principles that also apply to SDA deployment, all right? So if you look at underlay connectivity attributes, it's kind of very obvious that because Fabric is the overlay, it relies for underlay for transport, which means the underlay ideally needs to be homogeneous, right? It needs to be the same. Otherwise, you're dropping to the lowest common denominator. Consider this site where you have, let's say, a dark fiber between different buildings. So you can use, increased MTU, you can have multicast support, and then one particular building is connected through radio link with the lower MTU and without multicast support. What can you do? Well, you can either make everyone to suffer and drop down to these values campus-wide, or you can separate this building in a separate Fabric site so that most of your campus is enjoying high-speed underlay, and that building will be connected through this radio link on its own without affecting other switches. All right? So how would you carve your Fabric sites? Multiple Fabric sites or single? So far the answer was it depends, right? But my take on that, make the large single Fabric site within the same geographical area. Unless you start hitting the limitations, right? Unless you start hitting the device limit, for example, 1,200 logical switches for the single Fabric site, or endpoint limit, unless you have some problems with the underlay, MTU, or multicast support, unless you have a business requirements, such as part of your site needs to be online, even if remainder of the site is offline. Remember these borders? Borders and control planes, if they fail, the site is failed. How to solve it? Well, make it separate site with separate set of control plane borders. And importantly, part of your site needs to be provide direct internet access for users in the overlay. The users in a particular site are egressing through external border, all right? You cannot have unlimited number of external borders, it's only 4. And you cannot make part of the site egress through border A and another part to egress through border B. It's just not possible. So if you want to have this flexibility, it just needs to be separate Fabric site. All right? So if you look at Acme, guys, remember the requirement that we collected was 2,100 switches in 1,300 switch cabinets. Why do I care about cabinets? Well, because sometimes it's hard to find number of switch stacks. So everyone has an inventory of switches, but not everyone maintains the stack number. And stack is the logical switch, and that's what counts against the 1,200 logical switches limit. But in our case, we know that there are 1,300 cabinets, so there are at least 1,300 switch stacks, all right? Which puts us above the maximum limit for the Fabric side, which is 1,200. What do? Oh, we have to split. How can we split it? The first thought might be that, oh, I'll just make 2 Fabric sites, 700 switches in each, right? Well below the threshold, should be fine. But now we look at the topology. We already have 3 sub-areas which are pretty well defined. Why not make 3 sites to align with it? That's what we do. Unfortunately, every choice has a trade-offs, right? If you're not seeing a trade-off, it means that you're not looking hard enough. So in our case, the trade-offs are as follows. The subnet, IP subnet that you assign to the site, can only exist on one site. As a consequence of that, no seamless wireless roaming is possible, because when you're moving between the sites, you have to re-IP. Right? Each site needs to have its own set of border control plane nodes, because that's what defines a site. And importantly, an individual set of wireless LAN controllers. Because today, Cisco wireless LAN controller can only enable Fabric wireless for a single site. Right? And also, we need to have SDA transit control plane nodes. What are these and why would we care? So SDA transit is the idea that even though you split the sites into a few, or for example, you have a collection of sites, you can still glue them together so they have the same routing and security policy. Right? The way that it does it, it builds a VXLAN tunnels between the sites. All right? VXLAN carries VRF, carries SGT. VXLAN communication is the same as inside the single site, but this time it's going between the sites. Obviously, again, there are some trade-offs. What are these? Well, MTU, right? We're putting the traffic between the sites into VXLAN. VXLAN adds 50 bytes. So normal MTU needs to be increased. Dedicated transit control plane. This is just 2 extra Cat9K switches. It doesn't have to be big switches, could be just 9300s. As long as it should be just 9300. And If you have multicast in an overlay, so for example, you have sources in fabric side 1, receivers in the same VRF in fabric side 2, then you need to have multicast to flow over SDA transit, which means the underlay also needs to support multicast, but it's easy. It's just a source-specific multicast, so no rendezvous points, nothing, right? Okay, so we sorted our main site, right? We decided that we're going to split it into 3 subsites. We're going to use SDA transit. What about those 70 small remote sites? And again, there are options, right? There are always options. You can configure those 70 sites as each individual site, fabric site, right? Because the lowest footprint you can get to get SDA working is a single switch. You just assign all rules to that switch: border, control plane, edge node, and even wireless LAN controller, right? We call it fabric in a box. So let's look at pros and cons for each option. So in individual site, management overhead is high, right? We have 70 sites. It means that we need to create 70 sites. If you have 4 VRFs, well, we need to assign it to 70 sites. If each VRF has a single subnet, means you're now managing 300-something subnets, right? Each site will have eBGP peering per VRF, mind you. So that's 300 BGP peerings that you need to configure. That's a lot of clicking, right? On the pros, the servability is excellent, right? Each site is completely independent from another. So one can go down, this one is up. And each site can have its own routing policy. So if you want to have direct internet breakout, possible, right? An alternative approach is to have all the 70 offices as a single fabric site. So you would have to put a couple of head-end switches in a data center. They will run control plane and border roles. Then each site will simply have an edge node. Because remember, SDA is the overlay solution. It's the VXLAN tunnels between the switches, right? So pros are obvious. Your management overhead just reduced 70 times. Instead of configuring 350 subnets, it's 4 subnets. It's 4 BGP handoffs, not, again, 300. It's 4 VRFs instead of number of clicking, right? Obviously, there is no flexibility. It's very rigid design. There is only one way out through your borders, which are in the data center, right? And nothing else. And obviously, servability is low because if you lose these borders, well, all 70 sites go offline, all right? So to visualize it, here's the diagram. On the left, we have our data center. In the data center, we will put a couple of border control plane nodes. And we have our remote sites. Each of them has an edge node and a couple of APs. And each site will have a VXLAN tunnels all the way back to the border. OK, but isn't there MPLS in the middle? Yes, it is. Can MPLS be used as underlay? Absolutely. It's quite popular design, deployed in a variety of customer organizations. Again, the requirements are the same. You need to have increased MTU to accommodate VXLAN traffic. It's quite easy to do by MPLS carriers. They're usually happy to accommodate. Another one is a bit more tricky. So if you have layer 2 flooding requirement in remote sites, so when you need to enable broadcasts, then the underlay needs to support PIM, ISM, right? Sometimes carriers are happy to do it when they productize it, sometimes they don't. So it's something for you to check before you go with this design, all right? OK, so we have an understanding what we're going to do with 70 sites. Now, let's look at individual site. Let's zoom in on our main site, all right? First thing, when you log in into Catalyst Center and try to create the first SDA site, Catalyst Center will throw you a question. What control plane architecture do you want to use? Least pub sub or least BGP? All right? So I'm not going to go through this. I'll just say that least pub sub was released in 2022. All development on least BGP stopped at the same time. All right? So it had been 3 years now just for least pub sub development. We're releasing migration workflow for least BGP for legacy customers. But for Greenfield, the answer is always deploy least pub sub, always. However, there is always however. Last bullet point, is very important for you to keep in mind. All sites connected to SDA transit, remember that's a glue that connects all the sites using VXLAN, has to be on the same control plane architecture. So if you have just one site on ListBGP, all sites connecting to this SDA transit has to be on ListBGP. Or you migrate this one site to PubSub and then start doing all PubSub. So the migration workflow, so today you cannot migrate natively. You would have to unconfigure SDA with ListBGP and configure it again using PubSub. Engineering will be releasing migration workflow that can do it inline by the end of this year. So by then, ListBGP will be retired almost instantly, I'm guessing. OK. The next common question is, once you enable the control plane role on the switch, can you collocate control plane with the border? Commonly asked question. So, but before I answer, let's look at the resources, right, or scaling parameter. Border downloads all endpoint information and stores it as a TCAM, as a host route, right? Control plane stores it in a RAM, in CPU. So these two things are not competing with each other. Can you collocate? Of course you can. And in fact, that's a more preferred approach, unless you're hitting some scaling problems. So it's safe to collocate up until 50,000 endpoints. And again, this is the tested, validated number. If you have more, it might be also possible. Again, you need to get the approval from the SDA Design Council. You can still split it if you really want to for fault isolation, network modularity, non-scaling reasons. One thing that I really want to get across is that please avoid using routing platforms in SDA as a control plane or border. Because SDA is a solution that lives in switching IOSXE. Routing IOSXE is different, maintained by a different engineering team. So features come later. Bugs, fixes also come later. So please save yourself a trouble. Just don't use routers in any capacity in SDA network. OK? OK, so we configured our core switches, border control plane, that's fine. Now it's time to start enabling the rest of the network. But before we do that, there is another trade-off. How can we build our underlay for SDA? There are two options. We can use LAN automation, or we can build it ourselves. What's better? Again, the answer is it depends, but we will look at it. But before I answer that question, let's look what exactly do you need from the underlay, right? How can you configure SDA underlay? Well, you need to create loopback 0 interface, right? And assign it /32 IP address. So this loopback 0 is the VXLAN tunnel source and tunnel destination. So all the traffic in SDA goes between loopback zeros, right? Sounds simple enough. Then you can do some housekeeping, like you can bump the MTU, you can enable multicast. We'll talk about multicast a bit later. Then you create point-to-point routed links between every switch in a topology. Right? Again, you can use /30, /31, assign IP addresses, and advertise all of this in routing protocol of your choice. Right? Here I'm using OSPF, for example. Right? So creating OSPF and enabling links in OSPF in loopback and the point-to-point links. Sounds simple enough, right? Then we can enable multicast. Again, people don't like enabling multicast, saying that it's complicated, hard to troubleshoot. But it doesn't have to be too complicated. All right? As you can see, it's just 3 lines to enable it. You simply configure, you simply point it to the Anycast RP. You create the source interface, and you enable source-specific multicast. Sounds simple enough, right? Then you need to configure SNMP and SSH access to the switch. So Catalyst Center can log in and start configuring overlays. That's it. That's your underlay. There is no magic dust or anything. Just point-to-point routed links and loopbacks and routing protocol of choice. Now let's compare 2 options. So we have LAN automation and do-it-yourself approach. LAN automation, it's a turnkey solution, right? There is a menu in Catalyst Center. You configure your core switches. You get Catalyst Center to enable discovery downstream from these core switches. It goes in. All other switches are just out of the box. So it can discover it. It can claim it. It can configure point-to-point links. It can configure multicast. It can configure BFD, MTU. all you really need, all right? The only nuance that you need to be aware of, it deploys a single level 2 area. And it's using ISIS as the routing protocol. All right? Why it's important, I'll talk you on the next slide. So with do-it-yourself, obviously you're doing everything yourself. Most organizations choosing to deploy OSPF. It's more familiar protocol, I guess, more skills on the market. And you can do customization. So if you want to do MaxSec, for example, you do it yourself, right? If you want to adjust BFD timers, default maybe not good enough, then you do it yourself, and so on, right? Maybe you want to do multiple IGP areas, which I'll touch on. So if we zoom in, the only difference really is the routing protocol, right? Line automation deploys ISIS. Do it yourself, most people deploy OSPF. Why is it important? So this slide is actually very important, and I would appreciate full attention, at least for the next 30 seconds, all right? So seemingly unrelated fact number 1. Lisp needs a host route in a routing table for the destination loopback 0 in order to send the packets to the destination, all right? It's a liveness check. If the loopback 0 host route of a destination is not present, Lisp considers the destination dead or missing, so the tunnel will never get established. Seemingly unrelated fact number 2 is that maximum number of, well, not maximum tested number of Cat9K switches in a link state protocol area is 250. It doesn't mean that you cannot go higher. You can. We have customers doing it. Yes, there is a slower convergence. Yes, there are some, CPU utilization might be higher than expected, but it's possible. It's not a hard limit again. This is the maximum tested limit. This is the number that BU stands behind. But what it really means, if you want to stay within supported boundary, and you have more than 250 switches, you need to do multi-area deployment, all right? And now, here's the trick. So with ISIS, if you start deploying multi-area ISIS, the level 1 areas act like OSPF totally stubby areas. So they will filter all inter-area routes, including those /32s that we need, and substitute it with the default route, just like OSPF totally stubby. What it really means is that Lisp will stop working, right? While OSPF, as you know, the default OSPF areas just allow all inter-area routes. The solution? There are 2 solutions. One, you can implement manually ISIS multi-area, and there is the nerd knob there that allows route linking from level 2 to level 1. That will work, or you can just deploy OSPF manually. So as you can see, sometimes you need to do it-yourself approach, be it through the scripting or through CLI templates. However, again, we will be rolling out OSPF as part of LAN automation by the end of this year. So this conversation will become moot, hopefully. All right? OK, so we did the unicast deployment for the underlay. There is one more consideration for the underlay multicast. So some people, again, in the design documentation, you might read that multicast in underlay is optional for SDA deployment. In my experience, it's not. Simply because multicast is required for layer 2 flooding to work. And I'm yet to see SDA deployment where layer 2 flooding was not required. If you have layer 2 borders, again, you need to have multicast ASM enabled. All right? And of course, if you want to have multicast support in the overlays, you have option of doing head-end replication, but doesn't scale well. Ideally, you want to have multicast in the underlay. So how would you do it? You don't need to overly complicate things. You can put RPs, again, for the underlay on your core switches. It's Anycast RPs. You can configure MSDP between them so to exchange the state information. And then there are these 3 lines that I showed you before. You configure this static RP on every edge switch and enable PIM on the interfaces. So it doesn't have to be too complicated. OK, so we built our underlay. The next step, well, we can start designing our overlays, right? There are a couple of gotchas there as well that you need to be aware of. I think as I told you before, broadcasts are suppressed by default in SD access. That allows us to build large subnets, right? Because typically, people stick to /24s, 23s, 22s. Why? Well, because endpoints constantly flooding, all right? And at some point, it goes exponentially worse. So all of this broadcast, all of this trash is suppressed by default in SDA, but you can selectively enable it. That's what's called layer 2 flooding, all right? However, the gotcha is avoiding migrating subnets as is. Make large subnets. Don't migrate as is. Why? Well, because there are a couple of limitations. Again, they're documented in the Catalyst Center datasheet. One of them is that the sum of subnets, so anycast gateways, if you wish, and pure layer 2 overlay, so it's an overlay without the subnet, cannot exceed 1,000 per fabric site. And that's on the largest Catalyst Center appliance. All right? On the smaller ones, it's less. Remember, we have our requirements gathering session, and we gathered that we have 700 VLANs. And I'm like, OK, fine, but 700 is less than 1,000. It even gives us some room for growth, right? Why not to migrate? Well, because there is another problem. So Catalyst Center, as an appliance, has a deployment-wide limit of 1.5 million of managed interfaces. That includes logical and physical. All right? You might think that 1.5 million is a very large number, but let's do quick math. So we have our 700 subnets, and I forgot to say that when you're creating a subnet in SDA, it creates 2 logical interfaces per switch. One is Anycast gateway, that's an SVI. Another one is the Lisp tunnel interface to do the lookups. All right? So suddenly now, if you have 700 subnets times 2 for interfaces, times number of logical switches, 1,300, and then we add physical switch ports, so 48 port times 2,100, we're arriving at almost 2 million interfaces, just like that. It would be really painful to find out halfway through the deployment that you maxed out your Catalyst Center appliance, right? So something to keep in mind. If we shrink the number of subnets, make them bigger, so for example, we go from 700 to 100 subnets, suddenly math checks out. So we have 100 subnets times 2 times 1,300 logical switches, switch ports. Now we are 360,000 interfaces, way below 1.5 million limit. Make sense? Cool. So we sorted our unicast, overlay unicast. Now the next problem, overlay multicast. As you can see, when you're enabling the multicast in SDA, you're enabling it per VRF, not per subnet. And you need to have an IP pool where loopbacks are created on every single switch. As a side effect, you need to reserve this pool per VRF. And if you have 1,000 switches in your deployment, it means the pool needs to be large enough to accommodate 1,000 IP addresses where you will draw it. All right? Both internal and external rendezvous points are supported in SDA. All right? However, my recommendation for overlay, always use external RPs. Why is that? Well, because of this little limitation that multicast route leaking is not supported on Cat9K platform. You can configure it, and it might even work until it doesn't. All right? So it works kind of inconsistently. Basically, feature is unsupported. So why is that? Well, imagine you have a scenario where you have 2 virtual networks, IoT and Corp. Let's say IoT network has CCTV cameras, Corp has monitoring station, cameras talk multicast. You need to join the feeds, right? The problem is if you have an internal RP, it means that you have multicast in both VRFs, and the flows has to be linked between the VRFs. But that exact scenario is not supported on Cat9K. That's why internal RPs, well, I don't recommend deploying them. Consider external RP, right, north of the fusion. So in our deployment, for example, we have a firewall that does route leaking, and then a separate box, which is multicast RP. And all the subnets are just in global routing table. Right? So there is no route leaking. It's all in one table, so everything works. Can you put RP on a firewall that does route leaking? Absolutely. If you are confident in your ability to troubleshoot multicast using firewall CLI or feature set. Right? OK, so we're done with the fabric. Can you imagine that? We already deployed it. We configured the underlay. We configured the overlay. Next step is to connect our precious fabric to the outside world, all right? Because people want to talk to the internet, to data center, to shared services. And there are some nuances here as well. Classic problem. The borders that connect to the outside world, they're active by default in SDA. All right? So traffic is split 50-50 if you have two boxes. All right? Then each box will establish BGP peering with the firewall. Remember, typically it's a firewall to enforce the security policies between the VRFs. The problem with the firewalls that by default, and each border will generate a BGP advertisement with identical ASPAS lengths, identical subnet, identical origin. So it's identical advertisements. The firewall will only accept one, typically the one that comes first, and will reject the other one. What it really means is that when you have half traffic going to red sends it there, firewall checks the next hop matches, traffic is passed. Another half of the traffic arrives to border green sends it to the firewall because it learns the default route from the firewall. But the firewall drops the traffic because the traffic is coming not from the design next hop that it's supposed to come. So firewall considers it as a spoofed traffic. Well, that's a problem. All right, so what's the solution? There are 4 different solutions this time, not 2. And I numbered them from the most preferred to the least preferred, at least in my eyes. All right? The most preferred solution for me is to make the borders active-passive as well. All right? So the way to do it for overlays is that there is this advanced button in border configuration, and there are 2 values that you can adjust. Border priority, that's a Lisp priority. The lower the better. By default, it's 10-10. That's why they're active-active. Right? So if you can make one border, let's say border red 1, it will attract the Lisp traffic to border red, right? The egress. You also need to make sure that the firewall never learns green unless red is absent. So you go to green, and you simply add ASPAS prepend in the same advanced menu, right? So by this, the firewall will receive 2 BGP advertisements, one with longer ASPAS route, so it will store it in a BGP RIP, but will never install it. It will only install it if the border red BGP advertisement disappears. All right? Then your borders effectively become active-passive. All the traffic will simply flow through the red. Everything will work. For overlays, remember, you still have the underlay. The underlay, you need to adjust yourself. It's not automated. Well, it's underlay. Underlay, it's your responsibility. Right? You'll typically adjust again, you will have a BGP here in underlay, so we'll do the same. And here you will have, you will adjust the metric, right? So OSPF or ISAS metric to have red more preferred. So that's option number 1. Option number 2 is to enable active-active forwarding in this zone on the firewall itself, all right? So ECMP. That's also possible. Every mainstream firewall on the market supports this. Right? Palo Alto, Fortinet, Firepower supported from 6.5. There are 2 problems with that. One requires interaction with the firewall team. Sometimes it can be challenging. However, if you're lucky and you are the firewall team, which sometimes happen, the next problem could be that you need to pay close attention how ECMP and multicast are implemented in your firewall vendor. All right? Because typically, multicast doesn't support ECMP. And if you have multicast flowing, and remember, you have RPs north of your firewall, so it has to flow, then you will have a problem. So that's why it's a solution number 2, as in less preferred for me than solution number 1 with active-passive, right? It's the multicast. If you don't have multicast requirements, then ECMP just as fine. OK, solution number 3. It's a classic, right? If firewall can only peer with one box, OK, let's put this one box between our borders and the firewall. So it's typically like a switch stack, because you still want to maintain some level of redundancy, right? You wouldn't put a single switch there, right? At least 2, right? And everything checks out without any extra configuration tuning. It will be still active from the borders, and it will be just a single link, single logical link to the firewall. Right? However, I don't really like this solution because, 1, it creates a single logical point of failure in your network. Stacked switch, It's redundant hardware, but control plane is 1. That's why you only have 1 BGP session. All right? So fat finger or any other issues, and you will have an outage for the whole network. All right? You also need to buy these switches, which is extra expense. No one wants to pay for it when you can just do a couple of clicks in a GUI and solve the problem the other way around. And generally, all this, like if you have, let's say, 10 VRFs, you would need to configure these VRFs here. You would need to maintain all these BGP peerings. So every single change will become more complex. More complex changes means high probability of error, which means network uptime goes down, at least from my experience. And the last slide, last solution. You might be thinking that, if I can stack the switches in the middle, why can't I stack the borders? So I only put this slide to say, please avoid doing that. This is the worst thing that you can do, because now you suddenly created a single point of failure for your whole SDA network. All right? Because stackwise virtual, well, first of all, it's a single logical box. Right? So now you run one single instance of control plane. Might be a problem. If you have some hardware changes, you need to take down the whole stack, or stackwise virtual stack, right? Also, things like ISSU is still not supported for stackwise virtual for SDA. So there are a lot of problems, and again, please avoid. Okay. Another interesting thing, which is not necessarily related to the firewalls, but came to my attention recently. If you're using LAN automation and you're deploying ISIS, you might be getting a routing loop under certain conditions in your network. So with list pub sub, the design documentation might tell you that you no longer need this link between the borders. Because remember, in list BGP, you need to have this link to configure IBGP peerings per VRF manually. But with list pub sub, you no longer need it. However, consider this scenario. You have ISIS. Your borders have BGP peering with the firewall. So firewall is advertising the default route to each box. Then each box is also part of the ISIS domain. So they're originating the default route into ISIS domain. The way that they do it, LAN automation put default information originate. We all know this command, right? Generates a default route. However, with ISIS, it doesn't exactly act like OSPF. Default information originate in ISIS acts like a default information originate always in OSPF. And it injects a default route regardless if it learns a default route from upstream or not. Which means, consider the failure scenario. The link from the border green fails. So BGP session fails. It no longer has default route from the firewall. All right? However, it still originates a default route into ISIS domain. Okay. Okay, then the traffic arrives to the pair of distribution switches, right? These distribution switches still have 2 default routes, one to border red, one to border green. Half traffic goes to red and egresses normally. Another half goes to green. Green doesn't have this route. Instead, it installs the default route from the red in the routing table. So it sends it back to this pair. Traffic arriving here, it was already hashed to go to green, so it goes to green again. Routing loop for you. So solution, well, keep this link between the borders, advertise it in the underlay, and then the traffic arriving to green will simply go to red directly, not through distribution layer.
Is there a reason to let that default route load balance between your border nodes there?
Well, borders are active by default. So they have to be load balanced.
At the distribution layer, those static routes?
Static? No.
You only have one firewall up there, right? So they're going to 2
The list pub sub architecture requires you to have a default route learned dynamically. Yep. Well, like in theory, I guess you can have a static, but then it will be even worse because you have a static here, but it's not withdrawn if the link is down.
I'm not actually arguing for static necessarily, just a way of waiting.
Yeah, look, there are some nerd knobs. There are some node knobs that you can play with ISIS. There are some route map conditions that you can put to withdraw this advertisement. It's possible, but it's unnecessarily complicated. Yeah, so single link will solve this problem. Yeah, And some general observations, the one that I want to bring your attention to, it's eBGP here between the borders and the firewall. It's provisioned with default timers, so 3 minutes whole time. And it's provisioned without BFD. So if you want to have faster convergence, please make sure you configure BFD manually. Right? It's possible just to add BFD commands to Catalyst Center provisioned BFD CLI. It will not override it or anything. Just do it. And then you will have a speedy convergence. OK, so we sorted question. Second.
If your upstream is not a firewall, it's a fusion router like SD-WAN router, and you have a true overload or active, do you have the same problem?
No. So the question was, if your upstream is SD-WAN router and not a firewall, would you have the same problem that I described? No, this is specifically to the firewall, because firewall doesn't do ECMP by default. But SD-WAN router will do it, unless you enable some firewalling features on it.
So would that be a beneficiary to keep both overload active instead of active?
OK, so the question was, is it more beneficial to keep the borders as active-active? See, normally the problem, the bottleneck is not the borders. The bottleneck is your upstream, right? So the borders are switches that are capable of forwarding terabits of traffic. Your upstream is SD-WAN router or firewall that is capable of forwarding maybe tens of gigabits, right? So the bottleneck is always there. So it's OK to have it active-passive. If it's a firewall. SD-WAN router doesn't matter. It can be active-active, can be active-passive. OK? OK, so we sorted our northbound connectivity. Let's look at southbound. So we still need to connect the users to our glorious SDA network, right? So when you're creating an SDA site, Catalyst Center will ask you a question about default authentication template. So this is the default config that will be pushed to all access switch ports in your network by default. So you can choose closed auth, which is the full-blown .1x and MAB, like no traffic is allowed until endpoint is authenticated. This is the only option you would use in production. Open authentication is similar to closed, with the differences that even if you fail authentication, you're still allowed. That's probably OK if you're piloting .1x, not good for production. None. None really means that there is no authentication. So all the ports have to be configured statically, just like we were doing it for the last 20 years. Switch port mode access, switch port access VLAN X. That's what you would need to do if it's a none, right? Still possible through GUI, so it's all like automated still. But no authentication means no authentication, right? So my suggestion is, yeah, you can always start with none. You can change it later. And my suggestion is, when you're doing a rollout, just migrate existing switch port policy first. All right? Don't try to do two things in once, Fabric and .1x. Migrate the Fabric first. If they have .1x, great, they can have it. If they don't have .1x, go with none, enable .1x later as a separate milestone or something. Okay? So we did our wired endpoints. Now let's talk about the wireless. So with wireless, it might come as a surprise for some. But if you want to have Fabric-enabled wireless, the wireless LAN controller needs to be managed by Catalyst Center. So you actually need to use this intent-based GUI in a Catalyst Center to configure your wireless LAN controller. You can have Fabric-enabled wireless mode and centrally switched mode for the same SSID applied to different locations. Or even if you have a site, let's say with multiple buildings in it, you can enable it per building, which allows you gradual rollout. You can have a mix of Fabric SSIDs and non-Fabric SSIDs, so centrally switched or flex, on the same access point. You can have Fabric IPs and non-Fabric IPs on the same wireless LAN controller. So flexibility is there. However, if you have, like my suggestion is keep wireless as is during SDA rollout. Once you've done the switching, then you can do the wireless. Why? Oh, because you cannot have seamless roaming between Fabric-enabled building on SSID, and the same SSID is the centrally switched SSID. Because they have different termination points, right? If it's a fabric-enabled wireless, clients are getting IP addresses from subnets in the fabric, from anycast gateways, right? If it's a centrally switched SSIDs, the traffic is tunneled all the way to the controller. Controller is outside the fabric. It's a different subnet there. So you have to re-IP, which means it's not a seamless roaming. However, it's still possible to do it. If you're pressured to enable fabric wireless, look at the scenario here, right? We have 2 buildings on the left, 2 buildings on the right. You can still have fabric on, let's say, on the left buildings and central on the right building, provided there is a RF gap between the buildings, all right? So when client is moving from one building to another across this empty space, there is no Wi-Fi coverage. It drops off, then it joins another network, gets another IP address. It's not seamless roaming. It has to re-IP. However, if customer invested in outdoor wireless, all right, in order to provide seamless roaming, then you cannot do it. Because client has to re-IP, but the wireless connection doesn't drop. So by the time it comes to the AP connected to the central, it still has the old IP address. It doesn't know that you need to re-IP. So it will be just black holing. So yeah, that's why my suggestion is keep wireless as is until we fully migrated the switch network, and then do the wireless. Question?
So if I understand correctly, and I think it's more on the previous slide, but you're saying like you can have, if you have 2 different SSIDs, say one for staff and one for guest Wi-Fi, you can have your same AP serve up both SSIDs, but have your staff be part of the fabric and have your guests be over the top and dropped off like on an edge firewall somewhere else?
Yes, correct. So the question was, can you have multiple SSIDs, one of them being fabric-enabled, one of them being centrally switched or anchored on the same access point? The answer is yes. OK, cool. So we're almost done with our high-level design, well, detailed design. And as such, we have summarized our key design decisions, just as a refresher, all right? So we're going to have a single main campus site split into 3 different fabric sites, purely based on the sheer scale of the switches. Because we're splitting the sites, but it's still part of the same campus, we're going to glue them together using SDA transit. We will be using collocated control plane border nodes on the core switches, all right? Because the scale of each individual fabric site is not going to exceed 50,000. We will implement one stretched site for all of stretched fabric site for all of those remote offices, because all the resources are in a data center anyway. So if data center goes down, all these sites become useless anyway. They don't have SD-WAN, they don't have direct internet breakout, and importantly, the MPLS carrier can support increased MTU to accommodate VXLAN overhead. And the customer had decided to deploy OSPF as the underlay, because due to the scale, they would still need to do multi-area design manually. And when you're doing manual deployment, you might as well do OSPF. And the customer is having different multicast sources and receivers in different virtual networks. So they will be using a set of external RPs in a data center to facilitate this traffic flow. OK, we're done with the design. How good is that? We submit the design. The next step, implementation. There are a couple of gotchas there as well. So there are 5 milestones. I'm not going to go through them in detail because they will be covered in subsequent slides. But first one is the building management stack. Right? We still need to build Catalyst Center as automation engine. One mistake that I see again and again, so Catalyst Center has 3 nodes if you're building HA cluster. All right? And this cluster operates on a majority basis. What it means is that if you have, let's say, 2 Catalyst Center appliances in DC1 and another one in DC2, and you lose DC1, you lose the majority in a cluster, which means that single box in DC2 will shut down itself. So there is absolutely no benefit of splitting them in this scenario. Okay? So if you want to have geographical redundancy, just use DR configuration, not high availability clustering. One thing to keep in mind that virtual appliance, that the one that you can have on AWS or ESXi. We're getting Azure as well this year. It does not have native HA or DR capabilities, so it relies on a hypervisor. So for example, if the host with this VM fails, the VM can be automatically restarted on another host. But you cannot have HA cluster with VMs or disaster recovery for that matter. Once we built our Catalyst Center, the next step is to integrate. Typically, you would integrate with existing IaaS, provided it exists. Question?
So for the DNAC, is it just to keep only one and one for DR?
Depending how much money you have.
Or three like
Well, my preference is always a cluster, simply because you can have better software upgrades and non-disruptive. Like if you lose one box, there is no disruption to your network. Whereas if you have one-to-one DR, it's always like a disruptive event and there is a data loss. But if you have a requirement for geographical redundancy, then yeah, DR is the only option. Yeah. Okay. So with existing, there are benefits if you want to integrate with existing IaaS. But a couple of things that you need to keep in mind that one Catalyst Center can only be integrated with a single IaaS cluster. So Catalyst Center cannot be integrated with multiple IaaS clusters, only with one. Once you integrate, you can reuse all existing authentication flows, just have SDA-specific profiles. However, the trick is that if you already integrated DNAC or Catalyst Center with IaaS and you start building your SDA sites, you cannot change IaaS anymore. Or in other words, you can change IaaS, but then you need to unconfigure all SDA sites, or at least change all authentication templates to none, so that IaaS is not involved. So the idea is, if let's say you have legacy IaaS and you want to build a new one, do this bit first before you deploy DNAC and integrate it with IaaS. So always integrate DNAC with the final state IaaS. Otherwise, you're in the world of trouble. Okay, so once we build our management stack, next step is to start rollout. Right? So we already have our firewall because remember, existing deployment was MPLS. They already was using firewall to do route linking between VRFs. So we deployed a couple of switches that will act as a core. We will enable control plane border role functionality. We can assign all the VRFs there, all right, and create all the BGP peerings for all VRFs. That's our first, most basic step. The next step, my recommendation is to have a couple of edge node switches, add them in, connect. This is your end state replica of your campus. Because the SDA site configuration, the complexity doesn't increase if you have 2 edge nodes or 200 edge nodes, right? Or 1,000 edge nodes. Because you can create all VRFs, all Anycast gateways, test all endpoints, including some exotic stuff like PC imaging, #1 problem, wake on LAN endpoints, #2 problem. You can test it all with just 4 switches. Because then you can scale it out to 1,000 switches. There is no difference. The SDA site config doesn't change, all right? So you can test it all. You can test the failover between the borders just with 4 switches. Then, if you look at our customer case study, you can reuse existing distribution switches if you want to. Note that distribution switches are not fabric enabled. They're part of the underlay, so all they need to do is to have point-to-point routed links, multicast, and MTU, all right? So they don't even have to be Cisco switches if you don't want to, all right? Then typically you would have a choice between deploying parallel access switches or converting existing access switches. That is only an option if you already have Cat9K switches. So this customer had 2960s. So the idea was to have parallel deployment. So you drop a switch. Once you add the switch and assign it to the edge node role, all the VRFs, all the VLANs, all multicast stuff, remember you already tested it. So it's just pushed automatically. There are no changes. From there, you can just start repatching the endpoints, all right? And of course, then rinse and repeat until you have all the switches done. Then you can drop the core and if you have stacked distribution, now you can unstack them because you do stack distribution for mlag, but there is no mlag. It's all routed links here. OK, that sounds too good to be true, right? Every migration works in a PowerPoint. All right? There is a problem there. The problem is this migration approach assumes that all your endpoints are DHCP based, and they can, once you repatch them to the fabric switch, they can get a new IP address. Well, that's not always the case. All right? Classic case, CCTV cameras. CCTV cameras, there are thousands of them per campus. They're all, for some reason, statically addressed. You cannot migrate the whole campus overnight. So at some point, you will have a problem that this building is on a fabric, this building is not on a fabric, but the endpoints are in the same subnet. What can you do? This is where you will use layer 2 border functionality in SDA, which allows you to stretch the subnet from the SDA fabric to the outside world. All right? So in our case, we'll configure layer 2 border with this VLAN. You will shut down SVIs for this subnet on your existing distribution. And it will be simply that it will be pure layer 2 network. It will hit any CAS gateway on layer 2 border and will egress through the new connection. That will work, provided you follow the 6,000 limit. Again, this limit can be breached if you get an approval from SDA council, design council. That was the case when you have any CAS gateway inside the border and stretching the VLAN out. Sometimes there is a need just to create pure layer 2 overlay. For example, those who worked with VPLS or ELAN know what I'm talking about here, right? So there is no any CAS gateway, because sometimes there are endpoints that are not using IP addresses. They're using their own protocol, for example, BACnet, Profinet, whatever, typically these industrial endpoints, they're still using MAC addresses. So you can use layer 2 overlay to facilitate that the gateway can be outside the fabric. Another use case for it is multi-tenancy. So let's say you're an airport or shopping mall. Tenants bring their own subnetting space. They never compromise on that. And they bring their own gateway as well. So you just simply give them the glorified VLAN that spans the whole campus, which is the layer 2 overlay. And they connect to this, all right? The moment you have layer 2 only overlays, you need to enable layer 2 flooding, right? Because ARP, DHCP now have to be enabled and processed. So, but when you enable layer 2 flooding in this layer 2 only overlay, you might have a problem. Why? Oh, because if you have dual homing, and most customers or businesses want to have dual homing, right, for redundancy, you have a problem that the layer 2 flooding packets are transmitted through the fabric, but spanning tree BPDUs are not. Right? So if you look at this topology, from spanning tree perspective, there are 2 links. But in reality, there are 3. So you just created a forwarding loop. Right? That's why this deployment scenario is not supported. So what's supported? Well, supported from a single box, right? So then there would be nothing traversing the fabric. So spanning tree would be accurately detecting that one link needs to be blocked. Or if you have a switch stack, right? So when you have 2 switches in a stack, then it's still a single switch from a logical perspective. And then you can do a port channel, or you can still have one link being blocked. All right? So the broadcast, I think I mentioned before, it's disabled by default. All right? You have to enable it for layer 2 only overlays. The way to enable it is, it's a single checkbox. Important thing that when you're enabling layer 2 flooding, see, it's not just enabling broadcasts, it's also enabling link local multicast. Even with TTL1, it will be still flooded across the fabric. All right? And it requires multicast in the overlay. So remember what I said about large subnets? You still can have large subnets for conventional endpoints, like laptops and whatnot, right? You can still pack them all in one subnet, suppress the broadcast there. Typically, layer 2 flooding is required for some ancient stuff. So I see it a lot in hospitals, for example, or some legacy AV endpoints. They need broadcasts, but not for conventional ones. So those endpoints that need layer 2 flooding, put them in a separate small subnet, because then, and enable it there, because then in the small subnet, All these broadcast rules apply. OK. The last step in our fabric rollout is the microsegmentation. There are a couple of gotchas there as well. All right? So one thing to keep in mind, security group access lists, so SGACLs, only apply to unicast traffic. You cannot filter multicast. You cannot filter broadcast. And you cannot filter, well, they don't apply to link local IPv6 addresses to and from. Right? Something to keep in mind. Some customers decide to do default deny in the fabric. So by default, the default mode when you just roll out SDA fabric, it's a default permit, which means everything is allowed unless explicitly prohibited. All right? That's kind of what most people do. Some more security conscious customers deploy default deny, which means nothing is allowed unless explicitly permitted. And that's fine, but there are a few gotchas as well. Right? One, if you're using LAN automation will push the enforcement, the TrustSec enforcement, on a fabric routed ports, so on a switch uplinks, right? Which is fine if it's a default permit. But the moment you enable default deny, it means that the traffic from unknown to the switch will be denied. And unknown is your catalyst center. It's your ICE. So you effectively lock yourself out. Solution? Well, first, if you're running the modern deployment, let's say if you're doing it tomorrow, recommended release is 2377, so it will not have this problem. But if you already rolled out, you're considering default deny, you need to delete this line manually, well, or using CLI template if you want. Right? Another consideration for default deny is the timing. So think about this. When you enable default deny in the fabric, the default deny access list is pushed to the switch by default, and it stays there indefinitely. Then, once the endpoint comes online, authenticates, the switch downloads a permissive access list that allows the communication. That permissive access list has a lifetime of 24 hours. And if time expires, the switch simply refreshes it from ICE. So what happens if ICE is down? Well, the access list timeout, right? They all timeout. The default deny still stays. So nothing can talk to each other. We can call it a fail close mode, right? Of course, workaround exists. So in iOS XE, you can configure static SG ACLs. And the way that iOS XE works is that dynamically downloaded access lists take precedence over static. Which means if you want to have fail open scenario, you configure some relaxed catch-all access list that allows communication in case all the permissive ACLs withdrawn. Question?
You mentioned earlier you can now DNS 2.0.
Yep.
The templating for the switch, but in that there's a critical auth
Yep.
mechanism. So if you're leveraging that, would that not?
Well, critical auth will simply put you in the right VLAN. But this is a default deny based on security group tags.
You have a critical auth ACL as well. Oh, but that wouldn't be an SG.
Yes. Yep. So even if you have critical auth, the traffic will be still denied if you're using default deny policy. Yeah, if you're using default deny policy, that's important. Because if you have a default permit policy, the permit ACL will stay there. It will not time out. OK. So we're at the end of our deployment, right? And there are some lessons learned. So from my experience, the most struggles that I have seen is sometimes meat and bone, right? Sometimes customers struggling with IGP design. I've seen it all. I've seen like when people doing it manually, they're not using automation. There are a lot of IP address mismatches. Sometimes it's the same loopback interfaces, addresses, things like this. They take a lot of time to find and troubleshoot. So please, even you're deploying it manually, the underlay, just use some scripting or use some CLI templates to automate it. Because scripts don't make mistakes unless they're programmed to do. And exotic endpoints. So wake on LAN, PC imaging. Because, for example, when you're doing a PC imaging, the endpoint cannot authenticate in .1x environment. All right? It's just the imaging. So you need to think and test how you're going to handle it. Same for wake on LAN. When endpoints sleep, authentication on the switch port is lost. So it drops back to VLAN 1. Again, something to think about, what to do, how to test it. It's all possible, though. Using ISIS without experience. So it's a classic problem. Customer using LAN auto, not even looking at CLI. It's all deployed, it's all working, deployed with ISIS. Then they have a problem at some point. Now they need to understand, is it ISIS problem? Is it a TrustSec problem? Is it a Lisp problem? Where do I look? Where do I start? So if you don't have ISIS experience, consider using OSPF. Migrating subnets as is. I think I talked about it, right? The math has to check out. You have 1.5 million managed interfaces in Catalyst Center. And if you're just carelessly migrating subnets in, you might hit this limit real fast. And then you would have to redesign your deployment. And the last bit is a bit controversial. Some customers trying to approach this project as transformational. All right? So they're doing everything in one go. Hardware refresh, Fabric wireless, transition to .1x, sometimes even changing shared services, all in one go. So you have the old world and you have a new world with all the bells and whistles in one go. I'm not saying it's impossible, but sometimes it's taking a lot of time to build, a lot of time to test. And the more time it goes, people move on, priorities change, requirements change. My suggestion is just to take a phased approach, right? Do Fabric first, keep everything else intact. Then do, let's say, wireless. Then do .1x, milestone by milestone, not all in one go. OK? Yep. Second?
Your .1x already implemented, and then you use Fabric.
Yep. So the question is, if .1x is already implemented and you're doing Fabric, yeah, then you just choose .1x as the default authentication template and proceed with the rollout. You can, yeah, if all endpoints are set for .1x, you're already kind of 90% there. OK. That concludes my presentation. Please like and subscribe, or rather, complete your session eval. And thank you.